కూర్చొని అది పెట్టుకోవటం అట్లా అటు సైడ్ మూవీ అవి తీసుకుని తెలుసు ఇది అటు సైడ్ ఇది ఎంత అలా తిరిగే కదా ఓన్లీ
ఉద్దేశం ఏంటంటే మొత్తం
మళ్ళీ ఇది అయ్యాది నాకు సెట్ కదా ఇక్కడ స్టేట్ ఉంటుంది.
ఓహో అట్లా
అయితే మీకు చిన్న క్లారిటీ ఏంటంటే బీబీఏ పిల్లలు మన కాలేజ్ స్టూడెంట్స్ కాదు. బీబీఏ పిల్లలు ఎస్ఎంఎస్ సంబంధించిన ఫార్మసీ లేదు
అయితే
moving from carbon nanotube to carbon nanotube network, and then functionalized carbon nanotube or polymer nanocomposites. So we will have a different approach or different type of those sensors. Sound is okay? I think some this is yeah, noise, yeah. Can you help me? There is noise in the sound. Yeah? Yeah, it's good. Maybe, yeah, it's still there. Okay, that's fine. So, carbon nanotube, in previous lecture we discussed about carbon nanotube. It's, like a simple you hold the docking CD, and you can have a tubular set that is called carbon nanotube. And carbon nanotube can be, categorized in single wall carbon nanotube and multi-wall carbon nanotube. Between these two, there is one more category that we say double wall carbon nanotube. I have not shown that one here, but either it is single wall, multi-wall, and between these two, just we have a double wall carbon nanotube. More than double, more than two wall, we consider like a multi-wall carbon nanotube. And here the diameter is like for first case 0.5 to 2 nanometer, and in second case it's 7 to 100 nanometer. Why we are talking about carbon nanotube here, different type of carbon nanotube? Because single wall carbon nanotube may have different type of electronic property depending on availability. So for example here, the single wall carbon nanotube can be armchair, zigzag, and a normal one. So in armchair case, they are metallic due to their special symmetry, but zigzag, they are semiconductor. And between these two, you have a chiral CNTs, depending on NM values. So that's why it means when we work with single wall carbon nanotube, we have to be very careful in terms of fabricating quantum resistive sensor. You think with zigzag, we can make a quantum resistive sensor? The zigzag carbon nanotube may be used for FPD devices, but it may be very difficult to have a conductive network to build a quantum resistive sensor. The first condition for quantum resistive sensor is that you must have a conductive network. So the principle of quantum resistive chemical sensor, or what is the mechanism for that? In this case, sensor resistance can be modulated in presence of any light. And if that happens in the form of quantum tunneling or quantum interface, that's define the quantum resistive chemical sensor here. And in this case, if you don't have a quantum tunneling or quantum interface, your sensor may not be very high sensitive. It may be selective, but it may not be very high sensitive. So to introduce the high sensitivity, you must have a quantum tunneling or quantum interface. So how do these quantum resistive chemical sensors work? So when we have, any analyte in the form of chemical or molecule that interact with carbon nanotube, and then it creates a junction that is called a tunneling junction here. So when we have a tunneling junction, so simply we see a tunneling current here. And if we don't have that one, then there is no electron transport. So either you build that one or break that one, both cases. Either you build that one or you break that one. If you break that one, you are enhancing the resistivity. If you build that one, you are decreasing the resistivity. So you can use both properties for sensing application. Doesn't matter you want to break it or you want to create it. And this quantum resistive sensor, they have some advantage. They have the high sensitivity due to quantum effect, and due to smaller size, they consume very less energy, so they can be operated with very like a small energy. And you can introduce selectivity either by modifying the surface or introducing some additional component there. And as I mentioned, means to introduce the quantum effect, we should have a nanoparticle or nanomaterial. Doesn't matter what type of nanoparticle or nanomaterial we will have. But in this case, CNT has some advantage because it has very, very high surface area and it's really conductive. And we talk about multi-wall carbon nanotube. And even we can play with the surface of carbon nanotube in a tube factory to introduce the selectivity. So when we talk about sensing, and then we have this carbon nanotube. So there are different sites where analyte will interact. So, like first intra-CNT, and the second is at the junction of CNTs, and third is at the junction of CNT and electrode. So at least we have three different active sites when we have just only carbon nanotube network. I'm not talking here about functionalized carbon nanotube or polymer nanocomposite material. I'm talking here just only carbon nanotube based network. So we will have at least three active sites. Now the question is, what will happen means how we can have intra-CNT. If you have a pure CNT, it may not have a chemical interaction, right? On the CNT, you may have some defects, and those defects can interact with the chemical analyte and introduce the sensitivity. And we can create different type of network. So for this CNT, it might be very difficult to have individual CNT for sensing application, and we talk about quantum resistive sensing. We can have FPD devices for single part carbon nanotube, but it can be challenging to have that one. The second is CNT random network. So in this case, simply you have a solution or a dispersed CNT and just prepare an electrode where you have a random network of CNT. So in this case, electron will transport through different channels from one side to the second side. And then you may functionalize carbon nanotube and modify existing network. Another example is here a polymer nanocomposite. So in this case, simply you mix carbon nanotube with polymer and create a polymer nanocomposite. So that's another configuration. So there are at least 3 to 4 configurations. First, a single nanotube. The second, carbon nanotube network. Third, you can have a functionalized carbon nanotube. And fourth, you can simply mix carbon nanotube with polymer or another material. Excuse me. So carbon nanotube, when we talk about surface functionalization, or because that's the sensitivity. So there are 2 basic approaches. One is covalent, the second is non-covalent. And in covalent also, we have 2 approaches. One is simply attaching the defective site or attaching your molecule to a defect. In second case, first you do a small functionalization and then on top of that one, you interact another molecule. Then we have non-covalent functionalization. So that's also very interesting chemistry here. Basically, it comes to the pi-pi interaction, and the molecule that will interact in a non-covalent form, it must have ability to create pi-pi interaction with carbon nanotube. Otherwise, it will not be able to make that non-covalent quantity. And here we can use means different type of molecule, for example, surfactant or some polymers too. Anybody has any example in the form of polymer that can interact with pi-pi bonding with carbon nanotube? Anyone? So mostly these biomolecules, they are very good. Like for example, DNA or RNA. They have on the backbone, they have some type of like charge, and those charges create a pi-pi interaction with carbon nanotube. We will talk about that one in detail in next couple of slides. So covalent or non-covalent, they have their own advantage because like in terms of like for example covalent, you can make a strong bond between carbon nanotube and the molecule that you want to have, and it can modify the sp2 bonding of carbon-carbon in carbon nanotube. So it will definitely change the electrical property of carbon nanotube because you are basically modifying the intrinsic structure of carbon nanotube. In case of non-covalent phosphorylation, you don't kind of like destroy intrinsic property of carbon nanotube, but you wrap it with another molecule. So there is no, there is no disturbance on sp2 bonding. And here you create a pi-pi stacking or van der Waals forces or electrostatic interaction to attach that molecule. And it preserves the intrinsic property of carbon nanotube, so it maintains the high electrical conductivity. That's very straightforward. So now the question is, which approach may be good or means which is better? So again, it depends on the application, what application you are looking for. So here some very simple experimental setup. When we want to do this, we want to analyze quantum resistive chemical sensor for sensing. So the first one, very basic, a simple dynamic mode one. So in dynamic mode, you can have, like a gas and then flow in a container. The container may have, like, for example, alcohol, chloroform, or any type of analyte, am I right? And then the analyte will come to the electrode. And here you can attach one more kind of like a tube, and you can dilute that straight. And you can have the concentration that you are looking for. And here you should know, means in saturated case, how much ppm or ppt, what is the concentration do you have? And that's a simple question of the chemistry. I think it's also a theory that will tell you how much molecule we have in saturated. But in this case, simply, you can tune the ratio of, for example, inert gas and the analyte, and then you can have a different concentration of your analyte. If you want to have a little bit more simple, so that is called a static mode, you can use injection method. The first experiment for CNT, that was done by injection method. Injection method has some advantage and disadvantage. Advantage is that you can precisely control how much you want to test. For example, if you want to test 1 ppm or 1 ppt, so then by injection method, you can do that. For example, if you just inject 1 microliter of analyte in 100 liter of the box, am I right? So simply you will dilute extremely that one. And that's how they did the first experiment where they test using graphene or carbon nanotube at ppb level. So both the experimental technique, they have their own benefit and their own disadvantage. Here it may be difficult to switch one gas to second gas every time you need to create vacuum or clean your chamber. But in previous case, simply you tune or just turn on, and you can have a new analyte. So now, what about CNT, how they work for sensing application? So first configuration, having a carbon nanotube network. So in this case, we have a different type of carbon nanotube. like here you will see that's a CNT 700. So CNT 700 is all are these multi-watt carbon nanotube, by the way. Like CNT 700 or 7000, that's a multi-watt carbon nanotube with length at least around micrometer. They are pretty long. They are not short one. Then we have the short nanotube, very short one, like you can see in this picture. They are the long one, they are the short one. And then you have chemically functionalized, like with the NH2, OH, or COH. So you functionalize your carbon nanotube with these small molecules. And that you can do with acid treatment and then following, like another presentation. So when you create this a random network of these carbon nanotube and you examine for sensing application. So here we expose this network to methanol, chloroform, THF, and here you can see like CNT-COH, longer carbon nanotube have a higher response for methanol, and always the CNT salt is not the best one. And in some cases, for example, here it's very hard to discriminate, but they are pretty close. But here, one interesting result that we do have, if you compare the random network with bucky paper. What is the bucky paper? Bucky paper is a dense network of carbon nanotubes. Simply you do the filtration of carbon nanotube, and on the top you create a thin film. That thin film is bucky paper here. So comparison to bucky paper, all this random network, they have much higher sensitivity. That's the one evidence. That random network are much better for sensing application here. The second question that we do have now, what is the impact of nanotube density? Like if we have a very dense network or a less dense network. So simply when you increase the density of carbon nanotube, you are increasing the conductivity of your sample. So here, in this case, like you see the resistance, like here 1 kilo ohm, 8.4 kilo ohm, 32 kilo ohm, 69 kilo ohm, and 1.1 mega ohm. So here this is the resistance of the carbon nanotube based on the density of carbon nanotube. So higher the density, lower the resistance here. And when this network, they were examined for sensing application, just simply to check how the impact of this resistivity will be on sensing. So here you can see that. This is less than 10K, this is less than 100K, this is less than 1 mega ohm, this is 10 mega ohm. So here this is showing you higher response relatively compared to the sample. But when it comes to the signal to change ratio, delta R divided by R noise, so then this 10K that have pretty high, and higher the resistance, lower the signal to change ratio. The reason is that when you have this higher resistive sample, you have a higher signal, and due to higher signal, the ratio of signal to noise ratio is small. So here you can see that one, evidence here for isopropyl alcohol. These samples were tested for different samples as well, and every here we see that it's pretty same trend. Higher the resistance, higher the sensitivity, and lower the noise ratio. So as I mentioned, means you see in carbon nanotube, they may not be very sensitive to different analyte, so we need to do functionalization of carbon nanotube. Here, in this case, one group in Korea, they use single carbon nanotube, and they simply first functionalize with P4BT, and then use the platinum, and then use platinum and PON. And here PON is polyoxomethylate complex. So simply they functionalize carbon nanotube with platinum polyoxomethylate complex here. And they use the random network here. I don't want to go in the detail of this chemistry. Just I want to say you that at the end of the day, between these two electrodes, the carbon nanotube network is functionalized with platinum polyoxomethylate. And the reason is that they want to introduce the selectivity for one particular compound. See here the results for different analytes. In first case, this is only carbon nanotube, so there is no response here. We are talking here about methane, 0.5%. For no P, 4VP, again, no response. No PT, no response. No POM, no response. But when it's come here, so you see a pretty high response. That is delta T divided by T. So a very selective for methane at 0.5% here. And at least when we have this different type of sensor, this particular sensor is showing really very high sensitivity here. So we introduce high sensitivity in a random network here. And here simply you can see on and off means this is first cycle. When you plug air, so simply it's decrease and increase and decrease here. And here this is our different concentration in the form of ppm. So even we are able to see a really good signal at like 100 ppm. I'm talking here. At least you see a clear signal. There is no much noise. Then simply you can extrapolate this one, and you can see means like this sensor is able to detect like below 50 ppm for methane. And here is the mechanism for this polyoxymethylate compound. How it introduces the sensitivity for methane here. So here CH4 oxidation generates beta-hydrogen, and then that results in the sensitivity for this in single one carbon nanotube. Now about the selectivity and stability. So here you can see the sample or the sensor is pretty stable. That's new one. After 1 month, after second month, though performance is a little bit decreased, but still it's at a reasonable value here. But in terms of selectivity, like this is about methane, it has completely opposite result for carbon monoxide and hydrogen. And it, like here we can say that like in previous example we use a little bit complex chemistry, but here it's a very simple one. We have this carbon nanotube random network, and then simply we do a draw casting of caffeine on top of that carbon nanotube network. And then when it dries, just you clean it, wash it. So what you will see at the end of the day, you will have caffeine at the interface or at the junction of carbon nanotube or carbon nanotube network. Here with EDS analysis, clearly we can see the content of nitrogen. That's coming from the caffeine itself, because caffeine has that nitrogen atom here. And then we expose these for different molecules, like here ethanol, toluene, chloroform, methanol, or acetone. Carbon nanotube doesn't have any type of like background, but this caffeine CN2, it has a pretty good background, and it's showing the high response for chloroform here. And we also test things like conductivity means with respect to caffeine deposition and before caffeine. So here you can see means that is before caffeine, here it's after caffeine. So we don't lose the conductivity in that case because we are using very small amount of caffeine at the junction. Here is the signal, very sharp signal for on and very sharp signal for the off when we expose to the inner gas. And this is about response time. Though we have really very high sensitivity for chloroform, the response time is here the better for toluene, better than for chloroform and non-toluene. Now the question is here, how do you consider response time? Any idea?
Response is very simple time. Usually, best response time is like the minimum time duration it should have the better response.
Yeah, so but to be more technical, at least you should achieve 90% of the signal value, and within that period, that is called a response time. You don't consider 100% or 50% or 20%. At least 90% of the value of the signal should be achieved. And we did a very simple experiment in a static mode, a simple light injection method in a big container, and we were able to see a response at least at 1 ppm. Here we can see a response for chloroform here, or non-methanol here. So at least we introduced some selectivity, some unique pattern, and then a very low detection limit here. The second thing is here, like number of cycles. So the baseline, when we do the sensing, baseline is also one very important thing that we need to consider. Because with the time or with the number of cycles, the baseline can drift. And if baseline drift, so that's not good for sensing application. So in this case, there is no drift in the baseline, and there is no drift in the peak point. So it's pretty stable and pretty good sensor for this volatile organic compound detection. In another case, what we have introduced, rather than this organic molecule, you can mix carbon nanotube with some conductive particle. So for example, here, this is just only one example, where we are mixing carbon nanotube with M03P nanoparticle. And these M03P nanoparticles, they have a very good catalytic activity, for example, hydrogen. And they may be very good catalysts for hydrogen sensing as well, though we have no test here. But in this case, first you can see a very dense carbon nanotube network, and here you can see the carbon nanotube, how it interacts with the M03P particle. And this is confirmed with XPS and EDS analysis, even XRD, that we have a hybrid structure where we have a carbon nanotube and M03P interacting together. And finally, we examined for different analyte here. And in this case, like this is, it's here. So we check for acetone, water, methanol, ethanol, isopropanol, chloroform, or toluene to different compounds. And we have seen that it's again a pretty, it can differentiate within these volatile organic compounds. Those selectivity is not very good here. But compared to pristine CNT, they are pretty better. They have at least 7 to 40 times higher sensitivity compared to the pristine carbon, multi-watt carbon tube network. And they are very stable too, like up to 300 minutes with different cycles. The relative amplitude remains same. And here you can see the dipole moment and the sensitivity, they are correlated together. So depending on dipole moment of the analyte, if we have a like an interaction with M03P CNT, and that's why it has a particular selectivity for that compound. What about mixing carbon nanotube with another carbon material? Here, like a carbon nanotube is carbon nanotube and fluorine. Two different type of nanomaterial. They were either mixed or play with the chemistry, did C60 grafted on carbon nanotube. So three different type of network. One is carbon nanotube, second is CNT grafted C60, and the third is CNT mixed with C60. And here resistance is like 5 to 2 kilo ohm, 8 to 3 kilo ohm, or 4 to 2 kilo ohm. So here you can see when you have simply mixed, it still is pretty conductive. But when you do grafting, the resistance is a little bit high here. And when you test for the sensing application, again, different volatile organic compound like water, ethanol, methanol, acetone, or toluene, or cyclohexane. So here you can see a pretty high response for cyclohexane compound. For this cyclohexane compound, we see by introducing these C60, we see really very high selectivity here. Now you will have a question, why we are analyzing or why we are testing these volatile organic compound molecules. So the basic application of these type of experiment or these type of sensor is again for electronic noise, and these type of molecules, they exist in human brain. Either it's healthy or it's unhealthy. Just it's a ratio of those compounds that's changed. But still, you will have these compound there. Especially these cyclohexane, for example. That doesn't come from the healthy human brain. It comes from the, if you have a cancerous problem. So that's about a carbon nanotube network. So we did different type of carbon nanotube network, either functionalizing, chemically functionalizing, or we can do non-covalent functionalization. Here is one example. Here we have this chitosan molecule, or you can say chitosan. So there are two different approaches. Carbon nanotube simply mixed with chitosan, and on the chitosan you have like a electrostatic charge, and due to that electrostatic charge, they interact. They don't means there's no covalent bonding. That's a non-covalent interaction, like due to electrostatic force. And then if you do the cross-linking, so this chitosan will wrap the carbon nanotube. Here you see the atomic force microscopy for these three different carbon nanotube. This is your pristine carbon nanotube. Diameter is around 10 nanometer. When you have this 5 chitosan plus carbon nanotube, so diameter varies from 10 nanometer to 20 nanometer. And the reason is here, we don't have really very high diameter because these carbon nanotube, they are not linear. They are still surrounded by, like an unbound chitosan molecule. But after cross-linking, the diameter of carbon nanotube go more than 30 to 40 nanometer. So the chitosan molecule has wrapped carbon nanotube here. And this will help us to create a very controlled conductive junction between carbon nanotube and carbon nanotube network. And here we prepare in a very simple way the sensor. It's an interdigital electrode, and on interdigital electrode you spray the carbon nanotube solution, and then we will have this carbon nanotube network here. And here these are representing three different electrodes with pristine carbon nanotube with chitosan, or chitosan modified or functionalized carbon nanotube. And then we expose these three sensors to different molecules. Here we have a very simple molecule, like we have the water, methanol, and chlorine. So these chitosan functionalized carbon nanotube that have very high response, relatively high response for water molecule in comparison to carbon nanotube and simple chitosan carbon nanotube. And here you can see the background for this chitosan functionalized carbon nanotube here. That's a pretty high response for the water molecule. And it's very interesting to have a selective sensor for water molecule. If you want to design an electronic nose, so you should have a different sensor. They are selected for different analytes. So that's what's pretty kind of an interesting result to us. In another way, like there is another molecule that is called amylose. So amylose has a tendency kind of like a helical structure. And then simply you mix with carbon nanotube, what will happen? This molecule wrap the carbon nanotube itself. Helically wrap the carbon nanotube. And here you see a simple one, that's a starch carbon nanotube, simple starch functionalized carbon nanotube. This is amylose functionalized carbon nanotube, and this is pristine carbon nanotube. Here you can see, if you do the line profile for this carbon nanotube, so you can see high at particular gap. That will show that amylose is helically wrapping carbon nanotube. Like here, for example, here. So if you do this line profile on the carbon nanotube, so simply you will see these bonds. and that's coming from the amylose molecule. And when we test these for, again, those three different molecules, water, methanol, and toluene, so these amylose functionalized carbon nanotube again have the better response compared to two other networks. So here it is just confirming that if you are able to tune the junction of carbon nanotube and carbon nanotube, you can enhance the sensitivity. And even depending on the molecule that you are using to tune the junction, you can introduce a novel selectivity too. So you are going to work together here. Now the third is the very simple structure that you can make. Simply mix carbon nanotube with the polymer material, right? So simply you do the sonication, you have polymer, put in the chloroform, and simultaneously put the carbon nanotube in chloroform, do the sonication, then you have a chloroform polymer carbon nanotube solution, and you spray that solution onto the electrode. So you create a network of carbon nanotube within polymer matrix. And spray technology is much better than simple drop casting or simple, like a layer by layer coating. The reason is that here, when you do spray coating, you are creating a kind of, like a very, very random network. That's what you don't achieve using drop casting. Because these micro droplet, they have, like a L04 Carbon nanotube. So wherever you have these droplet, that will be carbon dense. But when you have a combination of these two droplets, so there is a tiny junction, maybe a very small network. So you will have a very interesting network here for sensing application. And these are simple optical microscopy images of these droplets, how they work on the electrode. So in this case, we have used polycarbonate and 1% CNT or 2% CNT. And then we examined these PC1% CNT and PC2% CNT for different molecules here. Here you have methanol, toluene, and water. Just wanna make you confirm that when we have the polymer carbon nanotube composite material, the sensitivity is defined by the interaction of polymer with the analyte, not the interaction of carbon nanotube and analyte. So, and that you can figure out easily. I don't know you have heard about that one or not. There is a one term, Heisenberg, I think Heisenberg, solubility parameters. Something like that. Maybe I can't wrote the first name, but it's a solubility parameters. That solubility parameter can define how they will interact with the polymer, how these analytes will interact with the polymer. And depending on that solubility parameters, you can have a selective sensor for different analytes. So in this case means like you can see for PC1% or PC2%, PC1% and 2%, so they have the same response for methanol, but for other two, the PC1% have a higher response. And again, the reason is here because PC1% is more resistive compared to the PC2%. PC2% is more conductive here. Here it's about the number of layers. If you want to deposit 1 layer, 2 layer, 3 layer on the electrode or different layers, so one thing will happen. If you are depositing more layer, so up to one point, the resistivity will decrease or the conductivity will decrease. But after that, you will have a saturation and you will have a stable conductivity or resistivity. So here with the 5 layers, 10 layers, and 15 layers, we can see that these 5 layers, they have the higher response compared to the 10 and 15 layers. And again, the reason is same because 5 layers, with the 5 layers, we have the higher resistivity. So to design a sensor with polymer and carbon nanotube, it's always a good idea to control the resistivity or the conductivity of your sample in a precise way. That's another approach to prepare these polymer nanocomposite. Here you can use the layer by layer coating. Layer by layer coating, how will you do? So for that you should have one anionic and the second cationic polymer. If you use anionic and cationic polymer, then alternatively dip your electrode in anionic and cationic. So you can create the layer of a polymer on your network. And especially like depending on the whatever the density you are using into the solution or whatever the content you have in the solution, you may very finely tune the thickness of the layer. Very finely tune the thickness of the layer. Here, simple schematic that you do have here in the solution of PDBA plus and its SWC and PDXID minus. So automatically it will interact this one, and then you can do alternatively deep coating, and then you will have a fit in case. Here is the TM analysis for this sample here. So very thin film, and these black dots, they are showing you the conductive carbon nanotube cluster here. And then we check the electrical conductivity. So they are pretty kind of like 50 ohm to 2 kilo ohm, and the thickness of the film is 5 to 40 nanometer. So you can precisely control the thickness of the sample here, of the sensor here. And here it's about resistance and response to the water or response to the methanol. So here number of bilayers means number of anionic and cation. So you can see at least, for example, 12 layer response is here, but at 16 layer we have the highest response here for the 16 layer. So that's the optimum condition for sensing application, at least in this case. And then we examine for different volatile organic compounds. So we are able to see a very selective pattern. So very high response for dichloromethane. It's very, very hard to achieve, like a very good response for dichloromethane using standard polymer methods. But in this case, using those ionic compounds, you can have a very high sensitivity edge. So I think I'm done for today for this lecture. So simply to conclude here, we have introduced three different approaches. Either it's a carbon nanotube network, then carbon nanotube network functionalized with a small molecule or with particle interaction, and third is a polymer nanocomposites. So these are just some examples. If you see the literature, that's full of different research. They have used different polymers. Maybe, I know at least I have tested 17 or more than 17 different polymers for sensing applications. And then about the functionalization, you can play a lot. You can do a different polymer, different small molecule, different type of like cluster. It's just a lot of freedom there. The work I will present here in what we have done, we chemically grafted PCl, polycaprolactam, on the carbon nanotube. And we did that one, so that was very, very sensitive to growth forms compared with all sensors. Any question? Maybe a lot of questions. Yes, sir. Sorry.
Thank you, sir, for wonderful presentation. So, as you know, like the material which is depends upon lots of parameters like selectivity, sensitivity, stability, etc. So, is there any optimization protocol like should we approach for a particular material? How can we approach? Because we have a lot of options as we are seeing, even we can upgrade the functional groups to it. So, any optimization protocol for a particular material or particular device?
Actually, it's very complex here. When you are talking about polymer, so simply you can go for solubility parameters. That's one thing here. Solubility parameter for those polymers to the analyte. So in that case, simply you can predict that one particular sensor will be selective for that particular analyte. But when it comes to the compound, it's not just only solubility. It may be like polarity, for example. How much polar those compounds are. And again, it's like a polar interaction or polar non-polar interaction. So that will also, predict that it may be sensitive to that particular compound. So there are different approaches. There is no single standard protocol to decide that we will have a selective sensor for this molecule.
Another question, we have different materials sensitive to different compounds. So let us say we have a mixture of gases which has to be identified by a sensor. So as we have seen in particular slide, we have some 16 layers which has maximum response. What I mean to say is, can we have the stacking of different materials on a single electrode or single chip kind of thing.
Yes, you can have that one. Means you can have one carbon nanotube and one polymer, and carbon nanotube another polymer. But again, it's a non-covalent interaction. It's a ionic interaction because we use those surfactant type of molecule here. So they were able to interact with the carbon nanotube. But if you have that one, definitely you can do that.
Okay. In a single sensor, we can have multiple.
Yeah. Yeah.
But is it not tedious procedure, like making those layers?
Yeah, it is a little bit, but we need to spend the time for the research, right?
Yes.
It was a process means where you dip and then let it dry in the air, laminate it, let it dry and dip. And the solvent that we are using that's pretty easy to evaporate. So in one day you can prepare the entire sample.
So then, how we can control the thickness quantity and taking also? Every time we take the same amount layers to
Yeah. So each something means you know the density of the compound in the solution. So either you will have a dilute or you can make it more dense, right? You can put the more weight there. So depending on that one, you can control the thickness of the layer on your electrode.
And one more question is the functionalization, as you said. Is it easy because use CFDs, like we have use much properties, different properties. When functionalization happens, it has like excellent properties. But during the functionalization also, as you mentioned, polymer composites. So we, for example, what I'm saying is I want to detect ammonia. So I'm using selective polymer. So it's really good for ammonia. And if I'm adding CNTs, by selectivity, it is detecting simultaneously and the exam mentioning, so it's detecting methanol. So, like, while I'm choosing, I want to detect ammonia only. So I want the more performance of CNTs with polyamines. So how am I going to differentiate it? That will really be for us.
Can you repeat your question one more
Yes.
time?
For example, I'm using CNT, sir. CNT is I want to sense ammonia only.
Yeah.
But polymers, polyamine is really good to sense ammonia.
Yeah.
So I'm adding CNTs, polymers composite to sense ammonia. But what we expected is rather than an individual pani showing better selectivity rather than composite. So like while choosing it, how we can individually we are choosing. So individually CNT showing better function, CNT showing better performance. Polymer showing. When we make the composite, the performance was like not very like up to the mark comparison to the individual.
In your particular case, you need to think about the mechanism. What the sensing mechanism do you have here? When you work with a polyaniline, so it's not simple conductive network that should be sensitive. It's a doping level that play important role in that case. How the electron are transferred to the polyaniline or how the doping level is effective of polyaniline. And when you introduce carbon nanotube, maybe you are having more conductive network there, and that network is playing more dominated role compared to the doping. So that's why simple polyaniline that may be more sensitive, but when you introduce carbon nanotube within the network, then it's less sensitive.
And one more question is not only the polyamine, so when you said you can make a composite with small molecules also.
Yeah.
CNTs are very connected of the conversations. They are really good. What about the polymers? Polymers after some period if they start decaying. So when we make the composite, like will it survive that long? Because we did some tests, we need to really get good results actually.
Yeah, with polymer nanocomposite, stability may be issue when you talk about months and years. So definitely that issue will be there.
So rather than polymers, can we add metaloxide to CNTs and all?
Yes, why not? You can do that one. Like here we did the C60 molecule. Yeah. And the second was like platinum and polyoxo methylation. So that was also very nice example. So there are different mechanisms for sensing means, and it depends means what you are picking and what you are selecting. Like it's not just only solubility, it's maybe like for example doping level of one particular molecule, or maybe ionic infection. So there are different ways.
As you said, like while detecting with gases,
Yeah.
with this solution, like do we have to because especially in mimosas case they will evaporate. Like in 7 seconds only they will evaporate. Sometimes they will instill extra heat to generate that what do you call it, vapor or gas. So how do we know, sir, how much only it is detecting actually? For example, I am sending 5 ppm to that solution, gas. But how much is my medical detecting? How I'm going to tell them exactly?
That's a good question. Like we are not telling here that those 5 ppm is directly going to the electrode, right? We are telling that in a 5 ppm environment, the sensor is able to give a signal. So that's why if you have a chamber, and in chamber you have the 5 ppm. So it doesn't mean that all 5 ppm is coming to the electrode. So you need to specify your condition here.
We can test it like low level.
Yes,
Example,
definitely.
1 ppm to we can go up to 100 ppm.
Yeah.
So the response will matter. So how the response is getting better is that matter.
Yeah. And again, means like when we sensing field have moved a lot forward. These type of experiment they give like a very fundamental information. But you need to move forward in terms of like data processing. You can use principal component analysis to differentiate different molecules. Like for example, in this case, if you have 10 different sensors and you collect the sensing response, and even you see that means there is no unique pattern or there is no well selectivity. But you can do both data processing and you do the principal component analysis, for example, and then you will have a different cluster zone for one molecule. And you can see how it is, like differentiating those molecules. Yeah. Any more question? Then thank you. So we will see another one. What is that? So those who are biomedical who want to come on the lab,
ಯಾವತ್ತೋ ಮೆಸೇಜ್
those who want to visit the biotechnology lab, how many members want to visit, just write the name. So today, maybe after 5:15 like that, you can go. And they'll show you. Okay. Some question work. Today afternoon some class or tomorrow I'll plan. Plan like this. I was told that some of the students want to go little early, kind of thing. So can we plan like this? 12:30 to 1 we will have our valid. So I'm inviting one of the old students of JNT who did his PhD, and then he has his own startup on sensors basically in Hyderabad. So I'll invite him tomorrow as a chief guest. 12:30 to 1, a small validation. Okay.
Don't bring any snack inside the
When those things I want to
where you can later, but these photographs will be displayed. That photograph will be no, I captured
everything perfectly.
most of the cases.
That I
Everyone, please complete your quiz quickly. The session will start in 1 minute.
and some biological sensor as well. That's why it's not a particular chemical sensor, it's just only sensing application. So a pretty simple outline here. So we will discuss about FET transistor, the basic concept, and then we will discuss about graphene, why it is excellent candidate for FET application, and then some examples for chemical and biological sensing application. So we will cover both of them. So first question is, what is field effect transistor? So field effect transistor, that is a device which is controlled by voltage. So it is a voltage controlled device, and the voltage at the gate terminal controls the amount of current between source and drain. Here is a simple example. You will have a source, drain, and between these two, you will have the graphene. It's a 3D structure. In here, you can see it's a graphene panel, and on the bottom, you may have a back gate here. So source, drain, and this is your conductive channel, and you will have a gate here. So that is how a standard, a very simple FET look like. Previously, we discussed about chemical. So the question means what is the difference between these two, FETs and chemical here? So in first case, often it involves the surface reaction or absorption. So that's modified the electrical properties, and you have the signal. But in second case, the gate electrode that is often connected to or include the sensing element interact with the analyte and doping happen. So due to change the electric field, the conductance between source and drain will be modified. So that's a very fundamental difference. In first case, you are simply talking about resistivity or conductivity. In second case, you are talking about change in the electric field between source and that will result in a change in the conductance between source and drain. So what is the advantage? First case, very cost effective, very simple. Anybody can do that one and make a combination. But in second case, it's very, very complex device and it's very, very hard to fabricate, and we need special tools. Here, it's maybe less sensitive, but FET, they may be more sensitive compared to the CAN resistor. So here are some advantages and disadvantages for each technology. This is just, don't go through this slide. This slide maybe you can read at home. But when you write an article or draft any manuscript about FET, you have to be careful because there are a lot of characterizations that you need to do. It's not about just only sensing. Before sensing, you need to thoroughly characterize your device. And even after characterizing device, you can do some sensing experiment. And here are different kind of like checklist. Like for example, you need to do structural parameter or insulator capacitance, and then drain front in saturation regime. And then you have a lot of characteristics and additional detail. So you need to provide all things before you prepare a manuscript or draft for FET devices. Here is a link for this article. So that is published in Nature Protocol, and it provides the guideline for, like if you have any device, what to do with that. So FET, the three basic configuration. One is bottom gate or the back gate. In this case, for example, here. The second is a top gate, and third may be a dual gate. So in first case, you have source drain and a conductive channel, for example, graphene, and under graphene you will have a back gate contact here for back gate dielectric. In this case, your gate is on the top, and here you will have one gate on the top, one gate on the bottom. In second configuration, when we are talking about top gate configuration, that's more interesting relatively compared to others. And the reason is that rather than just putting a gate, you can put any liquid and it can work as a liquid gate device. So the second one is mostly or widely used for biological sensing application. About graphene, this picture is very, very famous one here. Whenever anybody will talk graphene, you will have this picture. This picture is telling you about graphene electronic properties, and it's about pure graphene. So here it's a cone-shaped structure. So it means the graphene, doesn't have any band gap there. But the graphene has ultimate surface to volume ratio and electrical properties like mobility higher than 100,000 centimeters square per volt per second. And it has the mobility of not only for electron, for hole too. It means n-type or p-type in both ways. You have that one. The challenge for graphene application-based devices, one is band gap limitation. If you have the pure graphene, then there is no band gap. And if there is no band gap, the problem is that you cannot turn on off the switch, or turn on off the sensor, or turn on off the FET device. The second challenge is about fabrication cost, and third is saturation. So at one point you will have a saturation, so you will not have any like a change in property. So, but the big challenge is here band gap limitation, and we are good because most of the times when we prepare graphene using, like for example CVD or other method, and when we put on the substrate to fabricate a FET device, so already we have some impurities on the graphene. And that will result to convert pure graphene into either p-doped graphene or n-doped graphene. So already you have that one. And as I mentioned, means graphene can be p-doped or n-doped. So here, for example, you see here, this region is hole conduction region, this region is electron conductor region. How will you see that it's a p-doped or n-doped? Simply you need to see this point, the Dirac point. It's from 0 to this side or 0 to that side. Depending on that one, you can find out if it is a p-doped or it is n-doped. That's very straightforward. First experiment. If you make any FET device, do this experiment, first one. And simply find out where is the Dirac point. And it will tell you what type of graphene do you have. It's a p-type or it's a n-type device you have. And about sensing mechanism here, so charge density that modulates the graphene due to charge transfer. So if you have n-type of molecule, so definitely you can insert electron into the graphene, or you can insert hole into the graphene. There are just two possibilities. And depending on that one, the electrical property will change. That's a very fundamental mechanism for graphene FET chemical sensors. A little bit history about these 2D material or the sensor for sensing application. The first one here, for example, is a graphene first reported, but the first sensor, graphene FET sensor, that was designed or studied in 2007. And then we have these graphene electrochemical liquid sensor, and then graphene optical gas sensor or cell activated gas sensor. We will not discuss anything about these 2D material. Today, just we will talk about some example based on graphene FET devices. We are not talking about any of these two other 2D material. These are also very interesting. For example, Maxine or PMDC, they are pretty interesting for semiconductor, for these biological or chemical sensing application. So the first is graphene FET devices for chemical sensing application. This is the very first experiment, 2007. And this experiment was done in a very, like a very, very specific experimental condition. They have very specific setup. And here you can see this relative hole resistivity for NS3 and NO2 carbon monoxide or H2O. It's both in positive direction or negative direction. And here the positive sign is related to electron doping, negative sign is related to hole doping. So depending on the molecule, you will have electron doping or the hole doping and then you have a positive or negative signal here. The beauty of this experiment that made graphene very famous. With their, like a data post-processing and extrapolation, they were able to see a single electron transfer for each molecule. So when a molecule absorbed on the surface of activity device, so there is a charge transfer. And when it dissolved, then again there is a charge transfer here. So you can see for the red graph, this is dissorption, this is absorption. So these steps, every time there is a one electron change here. And that's why the article is published in Nature, and that was the first article about graphene ability for sensing application. Again, very complicated setup. They use one TB magnetic field for this device here. But the question is here, the pristine graphene is chemically sensitive or not? That's a very basic question. And experimentally, it's very hard to answer that question. So, but with computational study, we can figure it out. So with my colleague, what we have done, we did the computational study with the pure pristine graphene. It's a suspended free graphene. And on suspended free graphene, when you add a molecule DCB or another molecule DMMP, so here DCB is 1,2-dichlorobenzene and DMMP is dimethyl phosphonate. The first one is electron donor and this is electron acceptor. So two different type of molecule. You put on pristine graphene. So technically, we should see the shift in the Dirac point. But here, we don't see any shift in the Dirac point. In second case, in place of pristine graphene, you put the pristine graphene on silicon oxide. Because if you want to fabricate the device, you should have this graphene on SiO2. But here, this is a pure silicon dioxide. So that's why there is no defect. In this case also, you see, there is no shift in the Dirac point. It means there is no electron or there is no charge transfer happen in this condition. In third case, what happens if we introduce the water molecule? Even if we introduce the water molecule, still we don't see any change in Fermi energy level. The result was very surprising, and it confirmed that pristine graphene on pristine substrate is not chemically active at all. So then, what happens if you use this pristine graphene on defective substrate? So here, in this case, you have the graphene, pure graphene, that's here, and then you have a defective substrate. So when you use the defective substrate, so you see a shift here. And then when you add the water molecule, there is a further shift. So what does it mean? It means defects in the substrate, they introduce the sensitivity in the graphene FET device. And depending on the molecule, DCB and DMMP here, you have a positive and negative shift from the graphene because they are electron donor or electron acceptor. So we will have a correspondingly positive and negative shift. And here it's a magnified kind of like a picture for this one. And here clearly we can see that graphene on SiO2, that's at 0.15. It means it's a p-dot tolerant. So if you put a pristine graphene on a defective substrate, already doping happened. And when you introduce another molecule, chemical molecule, then you see again the shift in the Dirac point, and it happens due to electron transfer between two molecules. Theoretically, the computational study suggests here, in case of DCB, the HOMO and LUMO, they are very close to the graphene one. But in this case, DMFT, the LUMO is far than the graphene one. So it means DCB will transfer electron easier or quickly in comparison to DMFT. And here, HOMO is highly occupied molecular orbitals and LUMO is lowest unoccupied molecular orbitals. So the conclusion from this slide is that if we have a graphene on defective substrate, then we can do sensing with graphene FET. Experimentally, what happened means when we have this CVD grown graphene and we make this FET device and we use the same molecule, DCP and DMFT. So here simply we can see the positive and negative signal in both cases. And here sensitivity was measured simply calculating the current between source and drain divided by initial current between source and drain. Delta ISD divided by I0. So now we are sure that if you have a defective graphene or defective substrate, we can have a chemical sensing properties. When we submit this article in Nano Letter, then reviewer asks a very, very tough question. That can you verify that if you have a suspended free graphene, that will be sensitive or not? Then we fabricate a device here. So these are the graphene on silicon and they are suspended. They are freely hanging. And when we expose this device to the DMFT and DCP molecule, so here you can see clearly there is no sensing signal. But this was not an FET device, this was simply chemoresistive device. But even with this one, we can confirm that pristine graphene on any pristine substrate is not sensitive at all. And here the mechanism is simple kind of like abstract graph, because whenever you write a manuscript, you need to provide a beautiful picture. So this is demonstrating that if you have a pure graphene and the gas molecule comes, there is no signal. But if you have any defective substrate, that molecule comes, so that you will have a signal. So either it should be substrate should be defective or graphene itself should be defective. Only then you can have the sensing device. There is another example, just it's just a follow-up here. When you have this graphene FET device, here CVD chrome graphene FET device, and here the width of the channel is 10 micrometer and length was 70 micrometer, and there is a constant gas flow rate at around 750 ppm. So we have P-type dopant NO2, and then N-type dopant NS3, N-type dopant H2O, and CS3OH. And clearly here we can see the Dirac point is shifted depending on the property of these molecules, either positive side or negative. So this is the one another way to find out if your device is sensitive or not. Either you study the ISD, means current between source and drain, and here simply you can study about this Dirac point shift. That's to include or to introduce some selectivity in the graphene device, graphene FET here. So here, this is a simple experimental setup. What they have done, they put the graphene, and on the graphene, then they have a metal organic framework. So this is a simple graphene setup, and on top of this one, they have this metal organic framework. So now here the idea is that if ethanol react with the MOF, then there should be a charge transfer from MOF to graphene. Only then you can see the signal. If there is no charge transfer between MOF and graphene, then you should not see any signal. So, and the reason is that the graphene just align these energy level, so electron can easily transfer from MOF to the graphene. That is the sensing mechanism that has been introduced here. And here are the results here. So simply here you can see in first case. So this is VDS here. So it's already P-doped. And then you have ethanol on and off. Simply you can switch, backwards, forward. This is your IDS, current between source and drain, delta IDS. And again here you can see when you do on, so signal going down and off 0. And this is kind of like experiment were run at gate voltage at 0 volt. This is about concentration. Even you can sense up to 5 ppm, even below than that. And here response time was 1.03 seconds and recovery time was 0.65 seconds. So using that MOF, a particular MOF, we introduce the sensitivity for ethanol, and there is a new mechanism for that. This is about dew gauge FET hydrogen sensor. Some of you are interested for hydrogen sensor. So in this experiment, what they have done, very interesting concept. Here you have two FET devices, 1 and 2. One FET device, it has just only platinum. That's a platinum gated FET. In second one, you have graphene modified with PD and Ag particle, PD and Ag nanoparticle. And then the first one is your reference, and this will provide you the signal. So compared to this one, what the is happening, that will be your hydrogen sensing results. And these are very, very sensitive for hydrogen detection here. Like here you can see clearly the ID here in milliampere in the first cycle very quickly go up, and when you put the nitrogen, it go down, and same way. This is the signal you can see here. Stage 1, stage 2, and stage 3. So injection of molecule or injection of hydrogen, and then you put the nitrogen. And these experiments were collected with 2000 ppm concentration of hydrogen at 125 degrees Celsius. This is another example about graphene FET for NO detection, nitric oxide detection in biological system. So why nitric oxide? Because it's very important molecule for cardiovascular system or immune response. And here we use a non-covalent pi-pi stacking of amine molecule. So amine molecule was immobilized on the graphene using pi-pi stacking. And when we measure the conductance with different concentration, so even if you add 1 nanomole, so simply we see a spark signal here. And depending on the molarity of this injection, we can see it enhancing the signal. So just having this molecule on the graphene, we have a very selective signal for NO. And NO was kind of like studied in different media, like in fetal bovine serum here, and here DNAM. I need to figure it out what is the full name here, I forgot it. But in both cases, this device is very sensitive for NO. This is about pin selectivity, because you should have a selective device. So here, the device has been exposed to different ions, and here you can see there is no response for all those ions except NO. Here it's a kind of like delta G divided by G, and clearly you can see it's highly selective for NO. It's not selective to other molecules or other ions. So very interesting device and very specific for NO detection. So those examples, whatever the example I provided, they were for kind of like a gas molecule detection. Now, in real life, for the biological application. So the first is graphene protein sensor. So in this case, you have a simple graphene, and on the graphene, you have like a absorption of IgE and streptavidin assay proteins, and that is increased by BSA protein. So here, the device here, you can see the simple experiment. In presence of PBS, it's a straight line. There is no drain current. But when you have BSA, it's a positive current, and when you have this assay and IgE, it's a negative current here. And it's also sensitive to the pH. Depending on the pH, the top gate voltage that's it, and it's gives you indicator that it's very sensitive to pH 2. So two things: one is sensitive to pH, the second is sensitive to the proteins here. And here the mechanism is there that graphene, this molecule, they inject the kind of like a charge to the graphene here. This is a particular device for exosome sensing. So here we have different molecules. So for example, graphene. On top of the graphene, then you will use the linker, PBASC. And with PBS, you will bind this anti-CD650AB and then the base, and then you will have this one. And here in this case, depending on adsorption and desorption, the Fermi energy level of graphene activity will shift. Here in a more detail here, you see here this like a graphene, and on the top of graphene is a P base, and on the P base you have anti-CD650AB, and it interacts with the exome here. And if you have PBS, you see here it's a largely shift to down, and then you introduce these exomes, so then it's shifted upwards again. So the P-base linker and antibody, they constitute a physical separation between exosome and graphene. So that's happened, there's a physical separation. So that separation creates like a dielectric layer between your graphene device and your analyte. So it's kind of like there is no response if there is no molecule within that layer. And here negatively charged this exome, that's cause positive charge accumulation in the graphene, and that's respective to the endoping effect of PDS, which results in a change in the Fermi energy level. And that's demonstrated here. Its a shift is larger, here shift is again smaller here. And here it's about the sensing result, how the sensitivity is. So depending on different concentration, like 0.1 microgram per ml or 1 microgram per ml, still we are able to detect these molecules here. So this was another example of functionalized graphene active biosensor for exome detection. This is very interesting here approach. In place of like a horizontal graphene, a simple graphene, people have used vertically grown graphene and directly on the SiO2 on the substrate. So these are vertically grown graphene, and on vertically grown graphene, you have these gold nanoparticle connected with antibody conjugates. So you have gold nanoparticle antibody conjugates with the graphene, and they are immobilized with these freestanding graphene. So change in the electrical signal from the activity sensor upon the antibody antigen binding, that's a basic concept, where antibody will bind to the antigen, and then the charge transfer will happen, and simply you should see the response for your device. That's a very standard approach. And here you see with protein, with the pro protein and without pro protein. So here we don't have those gold nanoparticle and stuffs, but in this case we do have. So here we have like IgG, so simply we see a signal here, and we have a 20 nanogram per ml, then again we see the signal. And this is giving you the result about with protein probe or without protein. So it's very selective when you have this pro protein for IgG. So those were a couple of examples about simple gate devices for biological sensing application. But most of the work is done by using liquid gated activity sensor. So what is the advantage of liquid gated activity devices? Number one, enhanced sensitivity, and number two, it's also capable to have a label-free detection, and it can be used for different applications for biosensing and chemical sensing as well. And liquid gate you can easily build on the device because there is no need to fabricate very specific thing. Even you can put a droplet on top of your device and put one electrode there. Still you can do that one too. And here you can use a different probe. So for example, in this analyte, you have these probes, and the probe can be antibody, enzymes, or DNA. And it can be used for different analytes. Just here are some examples here, for example, for different ions, nucleic acid, or proton. So depending on your probe, you can have a selective detection for one particular analyte. This is one example that is gold decorated graphene for glucose sensing. So in this case, for this activity device, so you have two injectors that is injecting in and that is injecting out. So using this technology, injecting in and injecting out, simply you can do the on and off for glucose sensing. That's why they pick up this injecting in and injecting out. So here you have CVD graphene on CU foil, and then simply, you transfer it using the wet etching method on your substrate and fabricate the device. And here, this is the example means you have here plain graphene device, then you have naphthalene coated graphene, then you have gold decorated graphene. So these are three different samples. So they have studied what will happen if we use three different type of these channels. So how they will be selective or sensitive to glucose here. And the results were very, very surprising here. You see here for the pristine graphene, so there is a very small change in response, a very, very small change. But AU decorated graphene that have at least 2,500 in percentage for glucose. So that's a huge sensing behavior here. And when we compare these three graphene, like a pristine, and this is your gold AU decorated. So again, these AU decorated have really very high signal here. Response time for pristine graphene is 58 seconds, and gold is 21 seconds. So it clearly shows that when you decorate graphene with gold nanoparticle, the sensitivity of FET is more than 2,000 times higher in compared to the pristine graphene. For the glucose sensing, they have not tested naphthalene coated graphene because it doesn't allow interaction between glucose molecule and the graphene itself. So for this application, just they compare this plain graphene and this gold decorated graphene. But all these three samples have been tested for different applications, like for example, if they are sensitive to pH or not. So there is a lot of work in this article. But the beauty of this work was having the switch on and off for glucose sensing. That's not always easily possible for this FET device. It's behaving like a CAN register here. You inject the glucose and you clean it, again you are getting like all these signals here. This is again means how the VG and IDS curve look like. So this is about pristine graphene and this is about gold decorated graphene here. So here glucose transfer curve for pristine graphene, here it's showing like an end doping. Here doping is pretty small, it's not very high. But here we see that conductivity, how it's changing, it's increased a lot relative to this one. In this case, we don't see that change in conductivity. And there is a clear explanation for that one. And this is about selectivity, how selective it is for glucose sensing application. So this is your pristine graphene. Here it's sensitive to pH mostly. Naphthalene coated graphene, that's very sensitive and selective for the pH. It's not giving any response to the molecule. And this gold decorated graphene, though it's a very high signal for the glucose, it still is sensitive to pH too. We can functionalize graphene in different way. As I mentioned, that's especially for sensing application. We should have that one. This is another approach where we have pi-pi interaction between graphene and this molecule here. And then we have this FMR molecule like a probe, and it will catch this PB2+. So what here we are trying to do with this device, with this graphene FET device, we are trying to detect PB2+ ion in the solution here. And especially these are like a for children blood lead detection here. So here you see this is a simple graphene channel without any consolidation, and this is with FMR here. So simply you can see it's around 4.5 nanometer layer with AFM. And here when we expose the sample to different ions, so the device is very selective for PB2+ ion. It has a very small response for different ions, but it's very selective to PB2+ ion, even at 0.5 nanomole per liter. So that's a very small concentration it can detect using that particular molecule. This is another example about ion sensitive field effect transistor. So here you have this a simple device. And in this device, the new thing is that they put one ionophore membrane on top of the graphene. And then in the liquid, you have this reference electrode between source and drain. So when you have the analyte here, so simply look at here, that there is a potential difference here due to interaction with these ions with the graphene device here. And here we can see the shift here in the Fermi level here. So IBS, that is monitored at a constant bias, and electrolyte potential was varied using this reference electrode. And then a potential difference appears across the interface here due to difference in ion concentration between the membrane and bulk solution. And then definitely we see a signal in the graphene active device here. And this is the way means how they fabricate it. They use a simple wet transfer graphene, then deposit on metal contact, and then do injecting. Then do mounting dies transistor to PCB, and then ionophore mixture, the membrane, and finally encapsulating with the epoxy. And then they slice it, and then finally you have this tiny electrode like this. So you can have multiple electrode, maybe 30 electrodes from one device. Very easy, very straightforward. And the size of these dies electrode is here 1.1 centimeter and multiply 1.1 centimeter. Here you see the signal for this ion-sensitive field effect transistor. And here we are talking about sodium ion, Na+ ion, with different concentration. So we see clearly a shift into this Fermi level here. And here the IBS, source drain current, you can see simply step by step decrease here. So the channel current IBS of Na+ Ia as FET versus V reference for different Na+ molar concentration. That's your first graph. And here it's a continuous measurement of Na+ ion. At here, V reference is 0 volt here. In terms of like practical application, simply you can use in the field. So for example, this is the device that they put in the aquarium for the fish. And then when they added some food here, so immediately the concentration of these ions jump high. And using this device, they were able to see when the fish need that food or not, or still they have some that one available or not. This is a very interesting mechanism for this biological sensing, a very unique one. So here they are mixing molecular electromechanical system with graphene FPD device. So this molecular electromechanical system is kind of like a cantilever, and this cantilever will interact with the analyte, and then based on the charge, it can take that analyte to the surface of the graphene, and then signal will happen. Like here, and they are made of like, I will discuss in the next slide. So this is kind of like a setup here. You have graphene, and then these cantilever, and then on top of this one, you have this molecular kind of like a wire that's perform electromechanical behavior here. Look like this one here, for example, here. So it has a multiple. So this is a kind of like a dibilant. So if you have anything on between, like a bulk solution and the graphene, and within this region actually. So then it's very sensitive region, the dibilant, whatever we say, because there is no problem of multifusion or migration of those ions. So in this case, this one, like there are 3 steps. First is biorecognition. So biorecognition will happen. In second step is a transcription. So it will take that ion and bring to within the dibilant here, within that region. And third, non-specific absorption. So then non-specific absorption will happen, and then you will see a signal. And here you can see this one, like the advantage of this particular device and in a standard device. So in a standard device, it's uncontrolled from distance. So there is no control in the distance. But in this case, you are able to precisely control the distance. The second is uncontrolled probe height, but here in this case, you have very controlled probe height. So there are some very, very specific features about this device. And you can play with this one. You can, depending on your molecule, you can change the height and change the length. So for example, here for FMR, it's 6.8 nanometer, and then you have this kind of like structure that height is 5.3 nanometer. On top of this one, you have 6.8 nanometer, and you can play in both ways. Either you enhance the length of the probe or you increase the height of this one, this base. And depending on this one, you can have a different sensing behavior from it. This is how it looks like. Depending on the potential, that is E0. If Vg is less than 0, it will push down. If Vg is greater than 0, it will lift up. So that is the mechanism that's happened within graphene, and that's divided here. And here, the diffuse layer is less than 1 nanometer here, the dividend that we are talking. So that's a very small region where we need to have this analyte molecule. And here we see the signal, very, very sharp signal immediately after adding from within here. And it's every time means you add it and you see a quick signal here. So we talk about means different type of this graphene FET for either biological molecule sensing or the gas molecule sensing. Here is one other work that's talking about graphene FET device and discussing about why defects are very, very important there. It's for gas sensing, not biological molecule sensing application. So in this case, if you have these dots, they are called point defect. Here, these are the lines, they are called line defect. So if you have this point defect, electron can flow, or they simply, they can avoid the dot and they can pass through source to drain. But if you have a line defect, it's very hard to pass through from source to drain. So that's why having a defective structure or having this linear defect in the graphene, they provide higher sensing behavior. So in this case, for example, you have the graphene ribbon having the linear defect. It's a graphene, and here is the pristine graphene. So pristine graphene have a very small response, but graphene with defect a high response, and then graphene with ribbon that have the highest response for tolving. Here the pristine graphene device that was made with mechanically exfoliated graphene having a minimum defect. But other two, they are kind of like a CVD defect. So if you know that the defects are important for the sensing application, how you can tune that one? One of the best way is the grain boundaries. You can play with the grain boundary, and if you fabricate a device with those grain boundaries, you can have the significant higher sensitivity. And when we grow the graphene using CVD method, always we get a polycrystalline graphene. So this is kind of like a fade color picture, and each color is showing one grain. And between these two grains, we have this grain boundary. So the first task is, and when you have this one like defective structure, so there is a big band gap here for this particular reason, for this defective reason. So there is a kind of like a big gap in the. So it's not very conductive. So the first task is here, how to grow the graphene with controlled graphene grain boundaries. So if you use the CVD technology and you use the atmospheric pressure, so simply in a particular condition, you are able to grow these kind of like a crystal, single crystal graphene. And then using the like a technology, you need to find out a good channel, and on that channel you can put the electrode and make a device out of that one. So in this one, you have one grain here, second grain here, and between these two there is a grain boundary. So if you are connecting your multimeter or the device to these two electrodes, so then simply you are studying the effect of these single grain boundaries here. And it looks like here with the Raman spectroscopy, clearly you can see here the defect here. This is showing that this grain boundary is very, very defective here. And other two stuffs, they are pretty clean. They are not really very defective compared to this one. And this is about selected area electron diffraction pattern, SAED. So this is your left brain, this is your right brain, a pure hexagonal thing. But when we have the brain boundary, so there is a kind of like a mismatch of 8 degrees. So it's showing you that the brain boundary is kind of like a defective structure there. And we tested this device for two different molecules, DMMP and DCB. So when we both, one is electron donor and second is electron acceptor. So obviously you will see a positive and negative signal. So here you can see in the brain boundary region, it's really very high response here. But for the brain, for this, for example, in this brain, it's not very sensitive. But brain boundary is really, really sensitive here. And then we simply, like you can calculate the resistance of this individual brain boundary using simple formula. And here it looks like if you put your electrode far from the graphene brain boundary, then the sensitivity decreases here. Closer to the graphene brain boundary, then higher the sensitivity. And the reason is that if you put far from the brain boundary, the domain, the graphene domain, that's contributing a lot for signal. But if you put the close, then only this graphene brain boundary is contributing for the sensing application here. Excuse me. Then we try to extract how much sensitive is the graphene region. And here you can see graphene is more than 800% sensitive compared to the left or right brain. And in short, then we did a lot of work. We did some computational study as well. And with the computational study, we figured it out. The graphene brain boundary works like a switch. And if those switches are closed, then you will see an abrupt change into the electrical property. And they are favorable sites for absorption of this molecule too. And this is in more detail here. So these molecules, analyte molecules, they interact with the defective structure of citrulline. And here you can see the electronic structure, how they are modified when you are in a defective region here. And this is about transmission effect spectra. And here, when you have this kind of like a grain boundary, so that's lying at the edge here, and that will give you very sharp signal when you expose to any molecule. Right? That's all. Time for question now. That's during growth process. Yeah. Yes, yeah. It's during the growth process. It's not, like you don't transfer that one. It's directly you grow on the substrate vertically. Like for example, there I don't know you have seen that one or not. Previously, like people have grown MOS2 or all these TMDC very precisely vertically on the substrate using the CVD method. So they use the same approach. So it is a vertically kind of like things, but still they are kind of like there is some interaction with that. It's not like they are one here. They are not too far.
So you want to vertically align this graphene.
Yeah.
And how we establish the contact vertically aligned? That's a disadvantage.
Simply cross on both sides.
Like this.
No, it's cross on both sides. Top to bottom. It's not like this, it's like this. So the graphene, whatever you will come under the electrode, so that will be crushed, right? But remaining part, the channel is important here. The channel is vertically kind of like aligned. And it's not perfectly aligned, it's a randomly aligned. Yeah. It's not perfectly like PMDC or carbon nanotube. It's a randomly aligned. Pardon? I'm not sure about that one, but you can find it in the link. You can read a complete detail about method. They have discussed in detail in supplementary method. Yeah.
My question is, sir, how did you observe that rainbow rates perfectly? Which equipment, with which equipment?
You see there means the Raman spectroscopy, am I right? So with the Raman spectroscopy mapping, clearly you can see there.
Is there any possibility to detect the rainbow rates using AFM?
With the AFM, it's you can see simply a change in the height, if there is some change in the height, like a tripod or like a bar, but you cannot confirm that this is a rainbow. Because with the Raman spectroscopy, you see this is a defective structure, am I right? So it's clearly visible that this is a rainbow here.
One more question, sir.
Yeah, go ahead.
Yeah, it may be city for biological faculty. You said, I mean, you have very well explained that gold incorporated carbon nanotubes. They are detecting very well glucose sensing.
Yeah.
So is it only detecting, or is it going to be interacting with the glucose molecule? And if it breaks the glucose, if it breaks the glucose, then we can use for medication purpose also. Like I got that time.
Yeah. Here we don't see a typical oxidation reduction reaction. Like when we do simple electrochemical experiment, right? So the glucose is converted to another molecule. But here that's not the case here. It's a simple kind of like a topic.
One more question, sir.
Yeah.
You have done some theoretical calculations like DFT calculations. Will you, if you have time, will you please disclose the basics behind the DFT calculations?
That's DFT calculation is done with from my colleague. I was a part of the experimental one.
Okay. If any feedbacks available and
Yeah, sure.
your person is working with you,
Yeah.
will you please help us?
Yeah, sure. Anytime.
Thank you. Thank you.
Yeah. We have two dedicated postdocs that work actually for machine learning and this computation research.
Thank you.
Good afternoon, sir. Thank you so much for your valuable presentation, sir. I have one doubt. You explained about exosome, PDS, and IG based sensors, sir. So, where can we apply those sensors biologically, sir?
Oh, that's anybody want to answer that one? Any biologists want to help me to answer that question? Can you repeat the question?
Where can we apply exosome, PDS, IG based sensor biologically?
What is the application to detect exosome here? That's the question.
And sir, can we apply that in vitro or in vivo, sir?
That's it in vitro, but if it is useful, definitely you can use in vivo too.
Sir, if it is in vitro, what is the temperature, optimal temperature conditions we can maintain?
These experiments were done at room temperature.
Room temperature.
Yeah.
Sir, when we apply enzymes, we have to first think about enzyme kinetics, sir.
Okay.
Enzyme reaction depends not only on pH but also temperature as well as substrate concentration, etc. So, on what basis we can choose the enzyme concentration, sir?
Can you repeat one more time?
So enzyme kinetics, enzyme activity basically depends on temperature, pH, and the amount of substrate we are going to detect in our sensing language, sir. So what is the concentration of enzyme we can fix when we prepare the sensor, sir?
So you are talking about enzyme.
How can we fix the concentration of enzyme when we fabricate the sensor, sir?
For immobilization, right?
Yes, sir, immobilization.
So it depends. It's like, for example, in this, you can have equal ratio, like one gold nanoparticle can have one enzyme. So in that way, you can pick up that ratio. And if there is an excessive one, that doesn't have any bonding with gold one, so simply you should wash away.
Sir, I have one last question, sir. You mentioned about IgG antibody and IgM antibody, sir. They are the major antibodies found in human immune system also. Can we apply this sensors for other antibodies like IgA?
I think so. But again, the question will be that gold connected to that one will be specific to detect that one or not. So again, antibody and antigen, that's a kind of linkage, right? So one particular is selected for one. So here in this case, whatever they use, that's particularly selected for that particular antibody.
Thank you, sir.
Sure. I need to read more biology.
As you said, like pristine graphene is not sensitive.
Yes.
But concentration of graphene is it easy, sir, comparison to CNTs actually? Making it composite, doping, like enforcement. Is it easy comparison to CNTs graphene? Because based on literature, what they said is functionation is not easy with graphene.
It's I will say, I don't agree with that one. When you have these graphene or carbon nanotubes, if they are pristine, it's very hard to do any type of like functionalization or anything. But if they are defective itself, then it's very straightforward to do functionalization. And especially for this graphene, if you grow graphene using the chemical exfoliation method, like hammer method, for example. So first you will produce graphene oxide, right? And you reduce the graphene oxide, then you have the reduced graphene. So if that's not perfectly reduced, already you have those functional group where you can play the chemistry. It will be very straightforward there.
That is reduced graphene oxide, no, sir. So graphene is like, I'm not saying both are same, but this is reduced from graphene oxide. So
Yeah.
obviously we use RGO only, most of sensors are. But as it comes to graphene FPD based transistors and everything, so the functionation has like mixed with metal and gold nanoparticles or anything. Is it easy, sir, actually?
Functionalization of mechanically exfoliated graphene is difficult. But if you have chemically exfoliated or CVD grow graphene or even graphene via sublimation, that's you can do functionalization easily. Yeah. I have done one work where we use the 70 Mason method to grow the graphene, and then we use non-covalent functionalization of that graphene on SiC substrate itself. So that's just straightforward here.
You said defect graphene like, can
Yeah.
work better. So
Yeah.
like we preparing some graphene through CVD. So it's like perfect. I'm just saying it. So can you make it to defective, like after getting the graphene?
First, you should not say it's perfect, it's already defective if you are using the CVD method. The second is means when you will go for the transfer process, etc., and it becomes more defective. So there's a penalty of room to do functionalization.
Thank you.
Sir, I just wanted to kind of talk, I mean, whatever comments I have just got to know. I just have two doubts in that. That when Sir explained that the glucose comes in pints and reaction happens, if it can kind of break it down, we can use that therapeutics like that. But I guess it's just an antigen-antibody reaction, sir. There, I mean, the confirmation changes won't be happening there. It's just antigen-antibody reaction happens and it just detects that. If glucose breakdown happen.
That's what I mentioned. It's not an oxidation reduction reaction.
Okay.
Yeah, there's no any electrochemical reaction happening like that.
Okay.
It's just simply kind of like interaction like
It just binds. Okay. And when ma'am asked, can we use IgA means, I guess IgA can't be, I mean like, sorry? Ma'am, you asked that it can be used in sensors. I mean, what do you think, like, I mean, what is your comment? Okay.
Sir mentioned about IgG
IgM antibodies, there are three other types of
Yeah.
antibodies also, right?
Yeah.
So I asked whether IgA can also be used in the place of IgG and IgM.
Okay, I mean, I was studying about different antibodies used in sensor applications where I read that IgA is not that preferable because the epitope binding sites, whatever IgA has, it has multiple epitope binding sites compared to IgG and IgM.
Because IgG is a primitive antibody, therefore there is a substrate with
Huh.
but IgA also it is binding to base pairs.
Yeah,
There are some immune reactions that occur in between pairs.
yeah.
If you are able to fix that,
Mhm.
you can complex mucus related.
Yeah. I mean, I just read the articles, I just wanted to kind of go. Okay, yeah, so.
Yeah, thank you. But just want to let you know, guys, in silent studying biology since 10th standard. So I have very less knowledge about biology. Okay.
Madam, I think so. Um, Based on the type of molecule what we have to observe, then we can go through the IgA to.
But you can apply
We can apply. From my side, we can able to apply IgA2 in the place of IgG or IgM based on the analyte what we are going to observe, what we are going to screen.
but when coming to the immobilization, not all antibodies may be suitable. So first they have to immobilize something. So that's what that question I asked, sir, whether they are immobilized, suitable for immobilization.
Madam, actually here sir told about the Orion, right? Gold nanoparticles. Immobilize the antibody on the gold nanoparticles. Or the IgG or IgM. From my side, I am telling that if IgA can hold by another nanoparticle, then we go for that. For example, silver nanoparticle can able to, if silver nanoparticle can able to show the binding effect with IgA, then we go for the silver nanoparticle rather than the gold nanoparticle. Practically or not, we don't know, but there is a chance like this.
This is sounds like this, yeah. That's a good one. So try it. Cool. Anything else? Then we are done, I think, for the lecture. I don't know what is the next we do have.
So, so I mean, as ma'am said, according to the nanoparticle we are binding the antibody, I mean, it actually depends like that. Ma'am has stated that. But I mean, when in biological analysis, whatever we're doing, it is just not immobilizing antibody onto the our polymer. It is about after immobilizing, whether when an analyte comes on bind, is it showing the correct interpretation that what we are expecting. But I just wanted to see that compared, I mean, whatever IgG or IgM is there are complex macromolecules which selective, I mean, it is more selective than IgA because IgA is a dimer, it has like multiple, I mean, epitope sites for binding. When we are immobilizing, after when we are given an analyte to kind of know the binding affinities and everything, it will kind of different things. So the standardization, whatever will be there, that can't be happened. Like we are using IgA, like immobilizing. So I just wanted to say, I will answer to that question. Right? Do you know the structure of antibody? Yeah. It consists of FC position and KP position. And you have to keep it in your mind that you always immobilize the antibody upon the nanoparticle at FC region. Then FAB regions are free to attach the antigen. So there is no problem at all. If either with the IgG or IgM or IgA, whatever the antibody, if you immobilize the antibody with a nanoparticle at FC region, then obviously FAB region is ready to attach with the antigen. But still the specificity will won't be there no matter. For what happened? What will happen? Your FC region is at the bottom of the Y, right? Okay. FAB region is at top of the Y. So if you mobilize the crystalline region to the nanoparticle, then it is easy. But now that is what multiple binding sites are there at that region. No, the top, the top of the Y for IgA compared to IgG and IgM. The sites have multiple binding regions. The clear specificity is there. When the multiple binding regions are there, you have to go to a specific analyte. What you are just using a specific analyte there. You are not using multiple analytes. If you are using multiple analytes, then there is a chance of that. But now in a biological sample, if you take blood, serum, or anything, we don't only have the specific part we are looking. We'll have a different thing, molecules also present in the sample we are taking out. So at that time, the same case will arise in this IgM2. Okay. You are telling that IgA is a dimer, but it is a pentamer. Which one? IgM is a pentamer, right? Yeah, but the ability of the IgG and compared to IgA, it has more higher ability than the same. I was just go through the literature, then you will got more knowledge about the analytes. Yeah, I'm just telling you some satisfaction. Thank you. So, this is to the question what you have.
Participants, you can have your lunch and we'll meet at the CNFT department for the lab, to be lab and the cytoeconometry. Please come to CNST department at 2 o'clock. We'll have the lab session there. You can have your lunch, take your tokens, and have your lunch.
One number తీసుకున్నా